Hello, students. Let me help you with your homework assignment. In order to do this homework, you're going to need those Doppler effect equations, the ones that we derived in class. So make sure you have those written in your notes. If you don't have them written in your notes, let me help you really quickly. Don't forget that, or wait a second, never mind. Title your notes, Doppler effect equations. I want to make sure you have these in your notes for the quiz. Okay, to use the Doppler effect equations, you need to know if the sound source is moving towards you or away from you. So in one case, let's just use an ambulance because that's my favorite. The ambulance is moving towards some observer, and the sound waves are stretched out behind it. So I'm going to draw a velocity vector for the ambulance, and I'm going to label that velocity of the sound source. Okay, and then there's also the velocity of the sound wave. Don't forget that the speed of the sound wave does not depend on how fast the ambulance is traveling. The speed of a sound wave is always constant. When the source is moving towards an observer, then you can calculate the frequency observed by the observer, which is F sub O. Frequency observed by the observer equals the frequency emitted from the source divided by 1 minus velocity of the source over the speed of sound. In this equation, I have the F subscript S, but I didn't label it on the model, and I want to. So I'm going to just draw an arrow to the siren. That is the frequency that the source is emitted at the siren. Okay, make sure you have that in your notes and make sure you know what these terms are. The second equation you learned in your CK12 online textbook homework was the equation for a sound source moving away from the observer. And in that case, the sound waves are stretched out and they're longer. So this ambulance is still moving to the right, but the observer is behind them. So there's velocity of the moving source, which is Vs. There is the speed of the sound wave, which is V. And there's the frequency emitted by the siren here. I forgot to draw the siren. That's the F subscript S is the frequency emitted by the source of the sound. And then there is the frequency observed by the observer, which is F subscript O. So let's write the other equation. When the source is moving away from the observer, then we're going to use this equation. The frequency observed by the observer is the frequency emitted by the source divided by 1 plus velocity of the source divided by the speed of sound. You must have these two equations in your notes to be able to answer your homework problems that I'm going to help you with now. Before I do, like I said before, you always, anytime you write equations that you need to use, define your terms. So I'm going to define them again and make sure you have it. F subscript O, which is here and here and here and here. F subscript O is the frequency observed by the observer. You can write that in your notes. F subscript S is the frequency emitted by the source. The frequency emitted right there at that siren. Emitted by the source. Okay, the next term I want to define, wait a second. I forgot to show you where that is. Frequency of the source is in the numerator here. And in the model, it's the frequency emitted from the siren there. Right up there. Okay, the next term I want to define is V subscript S, which is the velocity of the moving sound source. Velocity of the moving source. Oops, I'm writing words twice. And you see that in the equations right here. One more term that you must make sure you know, the velocity of sound, which is this V down at the bottom. Let me put that here. V equals the speed of sound, the velocity or speed of sound, which is constant. It doesn't change just because the ambulance or train or whatever is speeding up. It's a constant. Okay, make sure you know all of these. You don't have to have it memorized, just have it in your notes. Okay, problem number 1. Let's do it. Number 1 says, you can read it right off the screen. A train is moving at 25 meters per second. Let me make it a little bigger. There we go. A train is moving at 25 meters per second towards Cindy, who is standing next to the train tracks. The train horn is sounding. What frequency does Cindy hear if the train has a horn with frequency of 1000 hertz? Use 344 meters per second for the speed of sound in air. Okay, step 1 is always to write down the given information. And they tell you that the train is moving 25 meters per second. The train is moving 25 meters per second means the speed of our sound source is moving 25 meters per second. They say that the horn is sounding at a frequency of 1000 hertz. So the frequency at the sound source is 1000 hertz. And they tell us that the speed of a sound wave we can use is 344 meters per second. And they also say that the train is traveling towards Cindy, so that's towards the observer. Okay, have the given information. Step 2 is to write down what it is you're trying to find. We want to find the frequency that Cindy hears, which is the frequency of the observer. That's problem number 1. Okay, step 3 is always to draw a model. I'll put my model up here. The model shows a train, and the train, I'm going to draw the velocity vector above the train to show that it's moving at 25 meters per second. And I'll draw some wave fronts. The velocity of the sound equals 344 meters per second. Here's my observer standing stationary next to the track. I'm going to label F subscript O, which is the frequency heard by the observer, and that's what we're trying to find. And I'm going to label the frequency of the sound emitted is 1,000 hertz coming from that train right here. There. Okay, step 4 is to write the equation we're going to use. Oops, I said step 4, but I don't actually want to write it because I don't want that to get confused with number 4. I'll just write equation. And the equation I'm going to use is the frequency of the observer equals the frequency emitted of the source divided by 1 minus velocity of the source over the speed of sound. Okay. Step 5 is to plug in our known numbers into the equation, do the math, and solve it. So step 5 is to solve it. Let's do that. We're going to plug in the known values. Frequency of the observer is what we're solving for, so that stays as the variable. Frequency at the source was 1,000 hertz. Divide that by 1 minus velocity of the sound source is 25 meters per second. And divide that by the speed of sound, which is 344 meters per second. Okay, we plugged the known values into the equation, and now we need to do the math. This math is a little more complicated than our last problems. You'll need to know how to follow the order of operations to solve this. The first operation is to do this division down in the denominator. I'll use a calculator, of course. 25 divided by 344. And I get my answer. So the frequency observed is 1,000 hertz in the numerator. That stays the same. Divided by 1 minus, and then when I do the division in this red circle, I get 0.07267, blah, blah, blah. There's more. I'm not rounding to significant figures until I'm finished with the calculation. The second step in the order of operations is the subtraction in the denominator. So 1 minus that previous answer, and I get the frequency observed equals 1,000 hertz divided by 0.92732 something something. I'm going to round it off there, but there's something I forgot to say. In this step up here, when I divided, I got meters per second divided by meters per second, and that canceled out. That's why I didn't write any units here. I forgot to tell you, these units canceled out. So there's no more units in the denominator, and the units we're left with are only hertz in the numerator. And that makes sense because I'm solving for a frequency. Okay, let's do the final math operation, is this division here. 1,000 divided by that previous answer, 0.9273, equals 1078.36991 hertz. And you'll need to round it off to the correct number of significant figures. I'm going to change the problem I wrote to a point hertz. I didn't say that. But I want that to be a significant figure so you don't have to round so strong. So I'm going to round this off to two significant figures, which is only the first two digits. So the frequency observed is 1,100 hertz. Ta-da! There's my answer. Make sure that you follow along in your notebook so that you can use these solutions to help you on the quiz. Let's do another one together. Okay, problem number 2. A submarine is moving toward another submarine. You can see it on your screen. There we go. A submarine is moving toward another submarine at a speed of 9.20 meters per second. It emits a 3.5 megahertz ultrasound. What frequency would the second sub at rest detect? The speed of sound in water is 1,482 meters per second. There are 1 million hertz in 1 megahertz. I accidentally put on too many zeros. There we go. Okay, let's do it. Start with the given information. They tell you that the speed of the sound is the one submarine moving towards the other submarine. The speed of the sound is 9.20 meters per second. That's not the speed of the sound. I'm sorry, the speed of the sound source, not the speed of a sound wave in water. The speed of a sound source. And it's emitting a frequency of 3.50 megahertz. So that's the frequency emitted of the sound source. They tell you that the speed of a sound wave in water is 1,482 meters per second. Pretty fast, right? They tell you that the sound source is moving towards the observer. So make a note. Moving towards the observer. Okay, and what do they want you to find? You must find the frequency detected, which is the frequency observed by the other submarine. Let's draw a model. The model shows this here submarine traveling at a velocity of 9.20 meters per second, and it is emitting ultrasound. The frequency of the ultrasound is 3.50 megahertz. And the velocity of the sound wave in water is 1,482 meters per second. And the observer is standing, wait, it's not a person. The observer is another submarine. I'm so used to drawing people. So the other submarine observes this. There we go. Okay, the next step is to write down the equation you're going to use to solve it. Since the two sound sources are coming towards each other, we're going to use this. The frequency observed equals frequency emitted by the source divided by 1 minus the speed of the source divided by the speed of sound. And the last step is to solve it. So we're going to plug in the numbers that we know. We've got our known values here, and we need to substitute them into the equation. So the frequency observed equals the frequency of the source. Oh, wait, I didn't convert megahertz to hertz yet. I can do that really fast. Let me do that conversion over here, just over here on the side. I need to convert 3.50 megahertz into just hertz. So how many hertz is that? Well, they tell us that there are 1 million hertz in 1 megahertz. So I need to multiply by a million. 3.50 megahertz has 1 million hertz per 1 megahertz. So multiply those and you get this many hertz. There. 3.5 million hertz or 3,500,000 hertz. Okay, I got it now. So back to what I was doing. The frequency observed by the observer equals the frequency emitted at the source, which is really big, 3,500,000 hertz, divided by 1 minus the velocity of the sound source is 9.20 meters per second. Very slow. Do you think there'll even be a difference? I don't know. Divided by the speed of sound, which is 1,482 meters per second. Okay, let's solve this math. Let's solve this math. You're going to need to use order of operations. So for the first order of operation, do this division right here, and you'll get frequency observed equals 3,500,000 hertz divided by 1 minus, and then let me use my calculator to get this part. 9.2 divided by 1,482 is a very small number, 0.0062078. It's a very small number. My calculator is giving me scientific notation, but I just converted it here in my head. Okay, next step for order of operations is to subtract. So 1 minus that answer, I'll use a calculator. 1 minus my answer. And I get the frequency observed equals 3,500,000 hertz divided by 0.993792. I do not use significant figures until I get to the final end result. Don't forget that the units canceled out, and that's why I didn't write any units down here in the denominator. The only remaining units are the hertz in the numerator. Okay, the last step for our orders of operation is to divide. And that's how I get my final answer. The frequency is 3,500,000. Let me double check my zeros. 1, 2, 3, 4, 5. Okay. Divided by that answer. And it is 3,521,863 hertz. So you see, it has increased a little, just barely any. I'm only using 3 significant figures, so let's round this off. Let's round it off. 3,520,000. hertz. Ta-da! There you go. Okay, now it is your turn. I want you to try number 3 on your own. Number 3 has 2 parts, though. You can do it. I'm sure you can. You need to calculate when the sound source is coming to the observer and then when the sound source passes the observer. Then what is the frequency behind her? Okay, I know you can do it. See you later.